Hi, it's Mr. Olson, and today we're going to be taking a look at different ways that tectonic plates interact with each other at tectonic plate boundaries. So we're going to be drawing some diagrams, which are a great way to show what's happening and describe what's going on. We'll also take a little bit of time with Google Earth to see some places on our planet where these things are really happening. So for starters, we want to kind of talk about the two main types of crust on the Earth. We have oceanic crust and we have continental crust. And if you take a look, you can describe oceanic crust as being kind of like a brownie. If you think about a brownie, it's going to be very dense and dark. It's kind of thin. And that's a good way to think of oceanic crust because it really is dense, dark, and fairly thin. Part of the reason it's so dense is that it has a lot of iron and magnesium in it. The type of rocks you would find with oceanic crust are extrusive igneous rocks, especially basalt, which is a fine-grained type of rock. Now, if we take a look at continental crust, it's very much different. It's more like angel food cake. An angel food cake, if you've ever had it, is very light and fluffy and thick. And that's a good way to think of it because continental crust is way less dense than oceanic crust. It tends to be light colored. It's a type of rock called felsic igneous rock. It's quite a bit thicker. We can see that it's anywhere from 5 to 6 times as thick as the oceanic crust. The reason that it's less dense is because it has lower density elements like silica, oxygen, calcium. This type of crust is made from intrusive igneous rocks, and a good example of that is granite or rhyolite specifically. So as we draw the different diagrams, you're going to see that we're using really thin layers for oceanic crust and thick layers for continental crust. So the first type of boundary we're going to take a look at today is called a convergent boundary, and the prefix con means together. And so we're taking a look at plates that come together. We'll start off by drawing a pretty dramatic type of boundary, which is when oceanic crust converges and crashes into continental crust. So let's begin. What we would see is oceanic crust here is going to be kind of a thin layer. We'll label that oceanic crust. And it's going to be meeting continental crust. So our continental crust will be over here on the side. Since continental crust is higher up, it rides higher in the Earth's mantle, and it's a lot thicker and less dense. When the oceanic crust meets that continental crust, it's going to be very easy for this more dense oceanic crust to just tuck underneath. So it starts to dive down back into Earth's mantle. So here's our oceanic crust that's starting to dive and go beneath the continental crust. And our continental crust is going to be much thicker out here. So the continental crust is kind of moving towards the oceanic crust, and they're meeting head on. So this is continental crust over here. And it's going to be quite a bit thicker. Now we're going to leave the top open for right now. So our oceanic crust, I guess to make sure that we know that that's the ocean, we'll go ahead and put some waves in here. We're going to see a lot of cool features that result from this collision. All right, so first off, this oceanic crust, as it starts to dive down, it's going to heat up because the mantle of the Earth is very warm. And as it starts to heat up, it won't actually begin to melt. The plate has to get quite a bit deeper into the Earth until the oceanic crust itself starts to melt. And usually what happens is it will dive down for quite a ways, and then it starts to break off into slabs, and the slabs will sink back down into the mantle. However, what it does do as it starts to heat up is it will release a lot of steam. Think about this crust. It's been under the ocean for millions of years. So it's going to start releasing steam. The water in the crust turns into steam. So we're going to show this steam coming up off of here. We'll label that. And as the steam hits the bottom of the continental crust begins to melt. So we'll start to show some little blobs of magma that are forming here. This magma will pool together and create kind of a magma chamber. Now you can guess what might be coming above this. If we have magma underground, watch out. There's going to be a volcano up above. Now, this type of volcano ends up being very explosive, and the reason why is that the continental crust, when it melts, it's very sticky. Okay, the word we use is viscous. Viscous means it doesn't flow very fast, so the sticky magma that forms from the continental crust will trap the gases, trap that steam inside, and the gases can't move through it very well, so it becomes pressurized. And so it builds up a lot of gas pressure until finally it erupts. And when it erupts, we have the most explosive type of volcano, which is called a stratovolcano. And a stratovolcano has layers to it, layers of ash that get deposited first when it erupts. And then after the pressure is relieved and the ash is blown out, then you have lava flows that come afterwards and kind of glue the ash down. So with a stratovolcano, what you're going to see is that near the top of the volcano, it's a lot steeper. It has a steeper slope, and then the lower part is flatter. And the top part can be steep because the ash gets glued in place by the lava flows, but the lava doesn't flow very far. So the top of the volcano kind of builds up faster. So here's our big volcanic ash cloud. We would see that coming first, and then we would see some lava that flows down the slope afterwards and glues that ash in place. So we've created a stratovolcano. And it is very explosive. Okay, now let's go back underground for a minute here. There's a few more things we want to talk about. So the process of one plate going underneath another plate is called subduction. Subduction. So this zone where that's happening is called a subduction zone. Subduction zone. That word sub means beneath and duct means to flow. So it's flowing down beneath. One other really cool feature that we would see right here is where the two plates come together, we end up creating an ocean trench. So if we're taking a look on the Earth and we want to see some signs that we're looking at a convergent boundary between oceanic and continental crust, things that we would look for would be a trench at the edge of a continent and volcanoes that are located inland. Notice the volcano's not right at the actual plate boundary, and that's because the oceanic crust needs to subduct and sink far enough to heat up and start to steam. So by the time it finally heats up enough to steam, it's not going to be right here at the boundary. It's going to be inland a little bit. So let's take a look at where you might see that. There's a couple cool places on Earth we could go and see this. In fact, these are kind of all over the place. The one that we'll check out, we'll look at two spots here in the United States. Along the western coast of the United States, there's a very small tectonic plate here called the Juan de Fuca plate. And Juan de Fuca is trying to move towards North America. And meanwhile, North America is going in the other direction. So our actual boundary is right here along the edge. And then if we move inland a little bit, we're going to see a huge string of volcanoes. And some of these are pretty famous. So here we have Mount Rainier. And here we have two more volcanoes next to each other, Gilbert Peak and Ives Peak, Mount Adams. Here's Mount St. Helens, which of course is very famous. Let's check this one out. You can see as we zoom in, it's got a huge crater that blasted out in 1980, and there's just volcanic ash completely surrounding that eruption. So if we were to move along the west coast of the United States, we'd see a whole string of volcanoes, and many of these are still active today. But an even better place to visualize this is a little farther north, where we see that the Pacific plate, an oceanic plate, is diving underneath the continental crust here at the edge of Alaska. And so this entire chain of Alaskan Aleutian Islands is constructed from many, many volcanoes. And I found one here called Mount Chiganagak. And we'll just zoom in and look at that. The reason I like this one is because it's very easy to see the crater at the top. And even though it's covered in snow, it's pretty obvious that that's a volcano. And if we zoom back out just a little bit and take a look at the boundary between the two plates, it's very clear to see that the continental crust here is very thick, and the oceanic crust seems to just disappear underneath at this very huge trench. So that covers our first type of boundary, a convergent boundary between oceanic and continental crust. Now let's see what would happen if we had two oceanic plates that were coming together, oceanic crust converging with oceanic crust. It's going to look very similar. Our oceanic crust is going to be coming along like this, and just like before, one of the two plates, now think about this, oceanic crust is going to be equally dense with this other piece of oceanic crust that it's converging with. So one of the two is going to end up tucking or subducting underneath the other. So here we have our two oceanic plates coming together, and one of them is going to subduct. Okay, here's our other oceanic crust going back over here. I'm not going to label them because from here on out, you'll know that when I draw a thin crust like this, that's oceanic. And if I draw a thick piece of crust, that's continental. So I won't label the crust every time. So our oceanic crust is coming here, and it's going to be subducting again. So it's another subduction zone. And notice again, I've left the top of this oceanic crust alone because we're going to see once again that as this oceanic plate subducts, it's going to steam. So here we have our steam being generated. And once again, the crust above that is going to start to melt. Now here's the difference. When we were melting continental crust, remember the magma was very sticky and viscous. It trapped the gases, and so it ended up being a very explosive pressurized eruption. Now in the case of oceanic crust, when oceanic crust melts, it's not very viscous, it's very runny. And that means that the gases can travel right through. You'd have steam that comes out underwater. And so this way the magma doesn't build up a lot of pressure. So when you have these eruptions with the magma coming from oceanic crust, it's not going to be explosive. It could be cool. It could be really what we might call a fire fountain. But when magma oozes out like this, we call it an effusive eruption. Explosive means it's very explosive. Effusive means it just kind of oozes out. And since the lava is very runny, it'll travel a very long distance. So what we're going to build up here is a different type of volcano that's very broad, very flat. If you look at it from the side, it looks like a shield. And that's what it's called, a shield volcano. So we're going to try to draw this as being very, very broad and flat. Okay, so here's our oceanic crust. We've made a shield volcano. Keep in mind, we're talking about the ocean, so of course there's going to be some water up here. And that means that even though we've built a very large volcano, most of it's underwater. And so what we end up with is a volcanic island. And oftentimes we're going to see a whole string of volcanic islands, one next to each other. Now, one other thing to point out is we still have a trench here, but since the oceanic crust was already deep and it dove beneath another piece of oceanic crust, it's going to make an even deeper ocean trench. So here's where we get our extremely deep ocean trenches. And to show this, what we're going to do is we're going to go to the deepest spot in the ocean. So let's head back to Google Earth for a minute. And this time we're going to go to Challenger Deep, which is the deepest part of the Mariana Trench. All right, so here we have a case where one oceanic plate is moving this direction. And actually, the smaller plate above it, it's kind of a diamond-shaped plate. It's the Philippine plate. It's going in the same direction, but the Pacific plate's going faster. So even though they're both going in the same direction, this is kind of like if you rear-ended another car. If you were speeding and crashed into another car ahead of you, that's really what's going on. But the Pacific plate's subducting and sinking beneath the Philippine plate. We can see here the huge deep trench. And one cool thing about Google Earth is it shows elevation data down here in the corner. And so the negative numbers mean depths. And I've found that we can get somewhere around 29,000 feet deep. I'm not sure the actual depth at the deepest part of the Mariana Trench, but it gets incredibly deep. There I found a spot where it's 29,127 feet deep. Wow. So that's what you would see as a result of convergent tectonic plate motion between two pieces of oceanic crust. All right. Let's move on to the back side of our sheet. And we'll take a look at a third type of convergent boundary now. What happens when two pieces of continental crust come together? One way that you can kind of model this with your hands if you want to is you can use a fist like this to be like continental crust. It's thick, and you can use the side of your hand like this to be oceanic crust. So if these two are coming together, like in our first case, we would see the oceanic plate subducts underneath the continent. If we had two oceanic plates coming together, one of the two would subduct underneath. Now in our third situation here with the two continental plates, we've got two thick continental plates of equal density. Neither one is going to subduct beneath the other. It would have to go way, way down to do that. So instead, these two plates kind of buckle and bend and push upward like this and create super tall folded mountains. So this one's a little trickier to draw. What we want to do is have a big, thick piece of continental crust over here, and another big, thick piece of continental crust over here. They're moving together. And as they come together, we're going to see that the plate bends and folds and buckles. See what I mean? It's tricky to draw. Bends and folds and buckles. If we looked at the layers of rock within this area, we would see that the layers of rock are also bent and folded. There would be many, many signs of metamorphism going on here. Many folded and bent layers. Now, would we expect to see volcanoes here? I would say not, because there's no way for magma to come up through the crust. So we wouldn't expect to see a lot of volcanic activity. However, we would see some strong earthquakes because these two plates just continue to push together and there's no give. So we're going to see strong earthquakes and folded mountains. Strong earthquakes and folded mountains. Now let's go ahead and check this out on Google Earth. So a good spot to go, we're going to go to Mount Everest. Go to Mount Everest, the tallest mountain range on Earth. I've pinned it. So we're sitting here at the peak of Mount Everest, and it's pretty crazy to see. Mount Everest gets a little taller every year as these plates continue to crash together, which means if you plan to hike Mount Everest, you better do it now because it's only getting harder, right? The mountain's only getting taller. Now, if we zoom out, we see a better pattern of the landscape, and you can start to see these folds. If we go to the north, we can see that these rock layers are kind of folded up into ridges. You're looking at, lines that go sideways like this that show that the land is folded and bent. and that continues farther out. All right, so I think what we'll do is we'll continue on. I was thinking about stopping halfway through and doing the second part of the video as a second part, but I think we'll just keep rolling because we're making good progress here. All right, so moving on. So those three boundaries we talked about so far were all convergent boundaries, cases where the crust comes together. We saw oceanic versus continental first, then we saw oceanic versus oceanic second, and finally now we just took a look at continental versus continental. Let's take a look at what the opposite of that would be. What happens when two tectonic plates move apart? That's called a divergent boundary. A good way to think of that is divergent, divide, split. Let's see what happens when two continental plates divide from each other. So what we're going to start off with here is two plates. Here's a continental crust here. And here's the rest of it. Up here, we've got another continental plate, and that's pulling apart. Now, since these two plates are pulling apart, what's happening here is a couple things. Think about this. If I had like a cut on a part of my body that flexed a lot, like my finger or my elbow, anytime I kind of move that apart, it's going to split and I might bleed a little bit. The Earth does something kind of similar. Anytime these plates split apart, that's allowing something to come up in between. Now, what could come up in between these two plates as they pull apart? Well, here's a hint. I've got red. So one thing that could come up between these two plates would be magma. That's an option. But since the plates are just moving apart, they're not, and there's no water involved, we're not going to have a lot of steam here. We would have kind of weaker volcanoes that form. The types of volcanoes we would see here would be called a cinder cone. So we might have some cinder cone volcanoes. A cinder cone looks like a giant pile of cat litter that you've scattered. They have a really large crater at the top. They're not held together with any lava really to speak of because the volcano is just going to spit out little chunks that will just scatter down. So we would maybe see some cinder cone volcanoes. But magma is not the only thing that would come out. Another option is that if the crust splits apart, you could have groundwater that comes out too. So I'm going to draw that because we're going to check out a place where that's the case. So we could also have groundwater that comes up between the crack. So a really good place to see this is in East Africa, the East African Rift Valley. A couple cool facts here. If you went to the East African Rift Valley, what you would see is some very long linear lakes. Linear meaning they're like a line, and they kind of trace the rift itself. So we would see some linear lakes. That's one side. And another fact that's pretty cool, as these plates move apart, think about it, the valley continues to get deeper and deeper. And so each year, as these plates move apart gradually, we're exposing deeper and deeper layers of rock. And so each year, archaeologists are walking along the valley and they're finding older and older fossils. And a lot of the fossils we find in East Africa are early hominid fossils. So they give us some clues into how hominids on Earth have developed. And as that rift continues to grow, we keep seeing older stuff. And so it's exciting that each new year there's more discoveries to be found. So let's head over to the East African Rift and see what we can find there for evidence. Okay, so here's our African Rift lakes. Now, before we zoom in, you can see that these lakes are very long and they follow a pattern. They're connected to each other. They're not physically connected to each other, but we can see that they're forming along the same way. And this African Rift continues up through here. Now, if we zoom in a little bit, Lake Tanganyika is a huge lake. I just pinned these here African Rift Lakes. Lake Malawi is a huge lake. Sometimes a group of these lakes are referred to as the African Great Lakes. We've got Lake Victoria, Lake Albert, Lake Turkana, and quite a few more. And the other thing that you would see kind of scattered around through these African Rift Lakes are some volcanoes. But again, they're cinder cone volcanoes. They're not super strong. And this is kind of the true Eastern Rift Valley right through here, where a lot of the fossils are being discovered. Oh, here's one thing we might be able to see. Look, it's the crater of a cinder cone. So we did manage to find one. And it kind of does look like a pile of cat litter, just kind of gray. You can see that it's just made of scattered pieces of volcanic cinders that get coughed out. Not a huge, impressive volcano like some of the other ones we've seen. All right, so we've got two more types of boundaries to take a look at. That was continent versus continent. So if you're going to do this with your hands, here's your two continental crust pieces. As they move apart, they're going to crack open and expose deeper and deeper layers and create a big, huge valley. All right, next, a divergent boundary between two oceanic plates. What happens when oceanic plates split apart? Well, here's one piece of oceanic crust. Similar thing is going to happen here. When the crust splits apart, it's allowing something from inside to come out. In this case, we are going to see that a lot of magma comes out. And when that magma erupts, again, it's an effusive eruption. It's not very explosive. It's just going to ooze out, and it gradually builds up taller and taller, which is why that we drew these plates kind of jacked up in the middle. It's almost like an underwater mountain range. So here we're showing the plates moving apart. Put some ocean on top. We'd have some magma from down below. You might be thinking, hey, this is in the water. Shouldn't that be explosive? Well, there's no plate that's really subducting and providing steam to the magma, right? And so we wouldn't necessarily have a gas-rich magma. So it wouldn't have to be pressurized. It wouldn't have to be explosive. But when these plates move apart, a little bit of the magma is going to come out, and it's going to harden underwater, and it's going to seal that up. And so what happens here, as that magma hardens, it's going to push these plates out to the side. And so if we started at this is called the mid-ocean ridge. We'll see that in a minute. If we started at the mid-ocean ridge, we would have the freshest type of rock right here, the stuff that just hardened, brand new rock. And as we work our way outward from the middle ocean ridge, we would see older and older and older layers of crust. So the older layers of crust are pushed outward. All right, so like I said, we're going to go check out the mid-ocean ridge on Google Earth. So in the middle of the Atlantic Ocean, what you can see is there's kind of a seam or a crack running down the middle of the ocean. And what's kind of cool is that that crack goes all the way up through Greenland and all the way to the North Pole. It kind of disappears up here, but you can trace that all the way down through the Atlantic, and it continues and continues until it hits a boundary of plates around the Antarctic plate. So it basically spans from north to south the entire ocean. Now, you also might notice that it's lighter colored in the middle. That's because the ocean isn't as deep there. And like we pointed out, this is essentially an underwater chain of mountains. Okay, this is called the Atlantis Fracture Zone. So it's breaking apart, splitting apart. There's the Mid-Atlantic Ridge. Not super exciting, but it is definitely a cool feature because it traces the boundary between all these different plates going down through the ocean. We have one left. Last one is called the transform boundary. Now, a transform boundary is different to draw. So far, all the drawings we've done have been from the side, like a side view showing the plates moving apart. And if we want to talk about a transform boundary, we have to look from the top. So we're going to call this a map view. You also can think of it as a bird's eye view. So if I've got two plates here like this, we're looking down onto the ground. One plate is going to want to move one direction, and the other one moves the other direction, and these plates slide past each other. Now, my hands are pretty smooth, but in reality, they would be more like this, where the edges of the plates are not smooth and even. They're kind of bound up with each other. So there will be times when the plates are trying to move and they might kind of stick, and then they would shift very quickly and stick again and build up some more stress and then stick and slip again. And that's going to give us a lot of earthquakes. So when we draw our transform boundary and look at the plates, one thing we want to do is make sure that we don't draw them as perfectly smooth plates. Let's draw them and show that the boundary between the plates is kind of jagged and uneven. These two plates aren't going to fit perfectly with each other. So there's one plate. And I'm going to show that they're offset. Of course, these plates would continue in both directions, but we're going to show them offset a little bit like this. And again, we want to kind of leave some gaps in between and show that they're bound up and sticking in some places, and they might have a gap in other places. So let's say this plate wants to move to the north, and this plate over here wants to move to the south. And we're in map view. It's one thing to point out. We're looking from the top, not from the side. All right, cool. So a good place where you would see this sort of action, really the famous one, is the San Andreas Fault in California. San Andreas Fault. Okay, now a couple things we would see here. So where the plates are locked together, they want to move, and they really only move like a few centimeters per year. But since they're not able to move, they're going to build up stress. So let's show that as a red dot. Here's a point of stress. And it's building and building and building. And when that rock finally breaks and the plates move really quickly all at once, it's going to send out earthquake waves. So we would have some earthquakes happening along here. Now, sometimes the plates just slip a little bit at a time and you have a weak earthquake. Sometimes you've built up stress over a long period of time and it's all released at once and you have a strong earthquake. So we could have weak and strong earthquakes. Now, earthquake researchers or seismologists are always trying to predict when and where an earthquake will happen. The one thing that helps is you can take a look along this whole fault and you can see spots where the plate has shifted recently. So we might say, okay, there's been a small earthquake right there, and there's been a small earthquake right here. Oh, and we had a couple small earthquakes here. So that's showing that this plate is able to shift and move. But if we have a spot in between where we haven't marked any earthquakes for a long time, that's what you call a seismic gap. So there's a pretty cool hypothesis that's being worked on. It's called the seismic gap hypothesis. I'll write it down here. Seismic gap hypothesis. Where you can kind of predict where we might have stress building up and large earthquakes in the future. Now, I want to point out a couple things. Since these plates don't fit perfectly together, that means that sometimes there is a crack and something can come up in between. Now, in the case of the San Andreas Fault in California, there's a couple cool spots you could go check out and see what has come up between the two plates. You could have tar and crude oil that oozes out, in which case you would want to go check out the La Brea tar pits near Los Angeles. Tar pits, trapping fossils from the Ice Age, trapping creatures like saber-toothed cats and all kinds of stuff. You could have tar pits. And I was out in California one time, and my aunt and uncle said, hey, do you want to go see the San Andreas Fault? And I was like, sure, I'm a big science geek, let's go. So they took me there, and we were driving through the desert, and it was really, felt like I was on Mars. It was just dirt and a few scrubby plants, but it just really seemed lifeless. We came around a corner and there was an oasis. So if you've seen a movie, people are crawling through the desert, they're just about dying of thirst, and they see in the distance, they see an oasis with palm trees and a pond and shade. And a lot of times it turns out to be a mirage. But in this case, it was real. The spot that you should go if you ever get out there is called Coachella Valley Preserve. Coachella Valley Preserve. Now let's go check out the San Andreas Fault in real life. And we'll see the Coachella Valley Preserve too. So San Andreas Fault is pretty cool to look at. Whoa, that's way too close. We can actually see it's stretching through the earth here. Big, long kind of crack. In some cases, if you look really closely, you can see that some of these valleys where a river goes across are offset because the plate has shifted. This part of the plate wants to move to the northwest, and this part of the plate kind of wants to move southeast. So you'll have offsets where things don't match up anymore. Look at how desert-like and barren it is around here. Now let's go to the Coachella Valley Preserve. That's the spot where the two tectonic plates have a gap and some groundwater has come up in between. So just to put it in perspective, again, it's just desert all around. Not much there. Sorry about the bell. But in the middle of the desert, we have all these huge palm trees, and there's a pond full of water here. You can walk around on boardwalks that trace around the edge, and there's all kinds of cool creatures that live in this area. You'll find little frogs croaking and squirrels. It's just a whole protected little habitat. One thing that we can do with Google too is we can do street view, so I can drop down Pegman here, and we can get a look at it from the ground. And this really gives you a perspective. Over here, barren desert, a few scrubby looking plants. And then if we look to the side, look at these palm trees. And these palm trees are huge and tall. And back in the palms, there's these ponds. It's just amazing. So if you ever get a chance, go check out the Coachella Valley Preserve. And you would be looking at a transform boundary. And that's the San Andreas Fault. So that covers most of the tectonic boundaries we're going to see on Earth. These are some good simple examples. Plate tectonics gets more complicated when you have multiple plates involved, like sometimes 3 or 4 or 10 or 12 tectonic plates that are all kind of moving with each other. But this gives us a good starting point. Hope you enjoyed the lesson. I hope you have some awesome diagrams, and I hope you have a great day. Thanks.